Yes. So, okay, then I guess then you are doing it. No doubt is there. Yesterday, yeah, for a long time we have talked about the doubts. Uh, Okay, so we'll go to the class right straight away. So, yesterday, first we started with the pin diode. Okay, and we saw that pin diode was useful for switching, fast switching, because of the low junction capacitance. It is useful and it gives better isolation as well as lower insertion loss. So how we use these pin diodes? So there are generally two topologies. So one is series configuration, another is shunt configuration. And most of the actual application, you generally need SPDT or single pole double throw. But yeah, here if you see the most basic application or most basic configuration which is possible out of a pin diode switch is a normal SPST switch. Just put a one single pin diode, so it will give you either on or off condition, right? And that might not be suitable for most of the application, because generally you want to have two different states uh, as well as matching. So and as we have talked, because in RF the matching is also important. So that is generally achieved through SPDT switch. And the most important thing in these switches is that you have to have not only RF microstrip lines or some other transmission line for RF propagation, you also need a DC biasing line, right? So that is what will make this diode switch on and off. So the moment you bring in a biasing DC line into a RF line, now you need to block the RF and DC in the different paths, so that only the intended RF path should have RF propagation and only the DC path should have the DC biasing propagation. So that's why this capacitance and RF chokes are necessary. That is what we have seen yesterday, right? So now going from here, so the two constraints what we have seen from this pin diode are that there are two different frequency terms. One is called transit frequency, another is called relaxation frequency or junction relaxation frequency. So generally these are the two terms used in the reverse and forward bias conditions of the pin diode, which puts a lower threshold of use of pin diode as a switch. So
Can you
generally
talk
these
a
are.
little loud? Your voice is not feeble.
Hello, how do
Can
you
you
hear
talk
me?
loudly?
Actually, I am talking loud only. So is everybody hearing me like this?
No, it's quite loud. No problem.
Yeah, exactly. So that is, I think it is a problem at your end. Please sign out and sign in again. So I think that will make it suitable. Okay, yeah. So the thing is, there are two different frequency, this junction relaxation frequency and transit frequency, which puts a lower threshold of pin diode as a switch. So generally these are in terms of megahertz. Okay. So higher frequency you can use, but in the lower frequency there is a problem. So what are the other alternatives? Okay, this is not even, as you know, this is not the only option. Okay, so there are definitely the other option is using a transistor, right? So generally whenever we talk about transistor, the first thing comes to our mind is the FET or the FET, right? MOSFET or even BJT and everything. So MOSFET particularly or the FET is particularly useful, or because there's an advantage that they have very low power utilization or low power consumption. Okay. So now we'll see like how to use a FET as a switch. So as you know, this gate drain and source configuration is there for a normal MOS any FET. And there is this capacitance between the drain and source. As you know, when the gate is forward biased, the drain and source will be shorted. And when it is, uh, when the gate voltage, gate to source voltage is below threshold, so it will be like acts like the channel is not formed, and it form kind of like a switch stop situation, right? So just by controlling the current, you can control the current between source and drain by applying the gate to source voltage. Okay, so that is the very basic of the any gate FET, and they are very stable and good to control, and all these things are there because as you know they have very high isolation between drain to source when you put when the gate voltage is below threshold. Okay, and because there is a low channel resistance, these switches you can operate up to very low frequencies down to DC. So that is one main difference corresponding compared to the other previous pin diodes. So these gate FET switches you can operate down to even DC frequency. Okay. So obviously, as you have seen, even normal DC voltages MOSFET or BJT you can use as a switch, right? And the reverse bias voltage VGS, it causes the depletion region. So that gives the what you call in their semiconductor terminology pinching of the channel. So because of that, the source to drain current is controlled by applying the voltage. And in the off case, obviously the channel does not get formed. And this mechanism, it ensures that we have a very good isolation at low frequencies. So these are again taken from this application note. Okay. So you can even read this yourself. So they will have more other content also. You can look into this. Okay. So yeah, before moving on, do you have any other question from this or even previous part until this? Yeah. Okay. So now to use the FETs for the switching condition, what we want, how to use them in our RF circuitry. So definitely, only one switch will not work because generally the configuration we are interested in is SPDT, single pole double throw. So only one gate or only one MOSFET will give you only one throw, one pole. You have only one way signal flow. But that we don't want, right? We want there should be two combinations. So for that, this shows a one type of configuration which uses four different FETs. Okay. So here also you see the common port is there. Okay. And you have to RF port 1, RF port 2, just as if you remember, same as the previous with the pin diodes. So common port means let's say signal is input through the common port. It should flow either towards port 1 or towards port 2. Okay, depending on the configuration of the switches. Okay, so how do we now control this using the FETs? So if you see all the fates are termed, FET1, FET2 here, and then FET4 and FET3. So definitely now what happens? So either you can, do a forward biasing or reverse biasing. So which combination you take will ensure that which way the signal will flow. Okay. So now see what happens. So when if we just want to switch off the RF from common port to port 2, if we don't want this signal to go to port 2, what will happen? We will FET1 and FET4 are reverse bias. Okay. Okay, and definitely FET2 and 3 are forward biased. Mhm. Yes. So if you forward bias FET2 here and 3, so that means the signal gets a direct path from common to port 2. Okay. And if you give give a forward path here, I mean, forward bias the FET3, so this port 1 gets grounded. And FET1 also on top of that, we are reverse biasing. So definitely from common port to port 1, there is no path now, no direct signal path now. But now FET2 is forward biased, signal flows directly to port 2, and FET4 is reverse biased. So that way this, path to ground is cut off. And if you do the reverse, so obviously the signal will, if you forward bias FET1 and reverse bias FET3, then the signal will flow from port RF port to common port to port 1. Okay, and you have to cut off the FET2 and short the FET4. Okay, so now if you see, by just taking these four combinations of these four different MOSFETs, you can control the same combination we had here. Okay, so this was the previous case. We had four pin diodes. Now we are using four FETs. But the if you see the topology almost remains same. Okay. Okay. Yeah, I hope you understood this part. Even the other one. Is there any doubt? Okay. Hmm. So the thing is, there are some differences here. Now here the biasing is not connected to the RF path. Okay, it has separate biasing itself because the gate control itself has a separate biasing. So that is why it is different from the pin diode biasing. You don't do not need to connect here the biasing line to the RF or microstrip lines to our other transmission lines. You can directly connect to the MOSFET itself. So I suppose if you use a MOSFET, they will come with a bit built up or some ports with for biasing. You can directly connect the biasings to them. Okay, unless unlike the pin diodes where you have to do it separately by soldering and all. Okay, and so that's why there will be no RF choke is required. The DC biasing path becomes simpler. And one slightly disadvantage is that on resistance of FET is slightly higher than pin diode. So if the on resistance is high, so if you remember the insertion loss, that is kind of like S21 related to S21 in the switch on condition, is slightly inferior for the FET switches compared to pin diodes. Generally, the pin diodes will have in the range of 0.5 to 1 or 2 ohm, but FETs have slightly higher than that. Okay, just a minute. Okay, so these are the comparison between two different type of switches, and if you see even here in this note itself, they give a very good comparison between different type of switches. So what are other options? Other options is definitely somebody was asking about IC switches. Those are there, and one other very important or popular switch I will say is MEMS or electromechanical switches, right? That is also there. And hybrid is like you use some of these in combination. Okay, so pin diode, and then if you have FET and hybrid and MEMS switch. So if you see the frequency range is pin diode starts from megahertz, and FET you can use even MEMS switches from DC itself. And the insertion loss, if you see, is very medium for a pin diode. That means good, and isolation is also good here. So switching speed is very good for pin diode again fast. So power handling is low. That is what one disadvantage for uh, mm, these switches, but MEMS switches can be used for high power operations. And yeah, as you see, like as expected, FET switches have very low power consumption, and pin diodes have on the other side high power consumption. Okay, and they have defined other things like how sensitive to stress and temperature, all this. So BEMS switches, if you know, they depend on the vibration and all, because they will be very thin, uh, nano or micro sized line lengths, which may change based on the vibration and all. Okay, so mostly pin diode works very fine, and if you want to use it for very low power and consumption, then you may have to go to FET switches and all. But generally, the size matters. If you have a very, let's say, millimeter wave switch circuit or terahertz, then obviously you cannot use them. Then you have to go to, let's say, IC or these MEMS switches. Okay. But otherwise, in our microwave, they work just fine. Now, coming to the application of these switches. So, one application is for making a phased array. So what is phased array? Phased array is if you have a composite antenna with multiple antennas together, so you can give defined amplitude or phase response to these antennas so that it will generate a beam steering or beam switching. Okay. So how you feed these antennas, antenna ports, that will decide which direction the beam is going. Okay. So that is also called steerable antennas. So there, to provide these phase differences or like defined feed phase states for the defined feeds, you will need a switch. Mm. So conventionally, like like very old days, what people used to do, even nowadays also, you must have seen a radar where the antenna or the radar whole system is rotating, right? You must have seen in ships or even near airports. You have primary or secondary radars which keeps on rotating or moving. Okay, so that is also one way of beam steering, but that's called mechanical steering. So there's, the new approach is called, or new approach is not so new though. It is quite like maybe still for half a century people are using, is electronic beam steering. So instead of moving this antenna system mechanically, we will steer the beam electronically. Electronically is how? By using these phase shifters or controlling the phase states of the antenna. So one approach is one defined, there are defined application. One is phased array antenna, where as I told you, the individual antenna or of the antenna array is feed. So mainly used in defense application or even civilian application like aircrafts. If you see the, do you know the uh, even the normal passenger aircrafts, like Airbus 320 or Boeing 738. So at the nose of the aircraft is like pointed sharp, right? So if you see in the picture, generally they have a very good, very big phased array radar antenna there for weather radar. Okay, so that is one application. So all the aircrafts generally comes with a weather radar at the front or the nose of the antenna, so that it can always sense the weather in front of the antenna. Okay, in front of the aircraft. Okay, and the other applications is smart or adaptive antenna. So what happens there is that for digital communication, the signal processing circuit, you need to feed the circuits with different kind of signals. So it not necessarily that you do only with phased array or only with this phase systems. You might have other kind of variation, right? So nowadays people use FSS or meta surface, this kind of things. Even that there also you will have some switches. By switching them, you can generate different beams or radiation pattern that might be used. in they might be called smart or adaptive antenna. Adaptive is why, so sometimes you can even sense based on the scenario, or you can switch between different scenarios, like you can have a different states, like different polarizations or different amplitude, different phase. All these things you can vary. Even it's possible to have different frequency itself. Okay, so those are called smart or adaptive antenna. So for all of these different applications, you need some kind of variation, or some which will be brought by these elements or switching elements. Okay, may not necessarily be the phase switching, but you have other elements as well. So coming back to the phased array antennas, so we'll see now a very basic configuration has two antennas. Okay, we have here, if you see in the right side picture, two antennas at spacing d, and at some distance at far field, we want to generate a beam. Okay, we, let's say we want the beam to be maximized at this distance. So generally, how do we calculate this? Let's say we start from a the very basic antenna, what we have, a Hertzian dipole antenna. Okay, so if we take the normal, you will find the electric field for a normal dipole. So if you have these equations of there is a constant which depends on the I naught. I naught is the current feed to the antenna, and here beta, you see, beta is the phase. So here we are taking both the antennas are with fed with same amplitude of current, that is I naught, but the phase are different. Okay, so this phase difference between them is the beta. Now, just by controlling this phase difference, we see how, what marvels we can do here. So if you see here, this, the equation here, we just add these two equations with 2 beta. So plus beta by 2 and minus beta by 2 is because, from the midpoint 0, we take one is beta by 2 advanced, another beta by 2 lagged. Okay. So that's why plus and minus comes. And the distances R1 and R2 is noted here. So what happens that we generally make approximation here. If you go to very far away point, then this theta 1 and theta 2 becomes almost same. Okay. So for this, the amplitude term, you can amplitude almost remains same. So this amplitude term R1 and R2 you can take as same equals R. Okay. That is one approximation generally we do for far field calculation. But the phase we will not take, because phase, even little bit variation may give you a lot of lot of variation there in your signal. Okay, so that we cannot do. But amplitude generally it will not change that much, because when the 1 by r is very less, it will be almost constant for R1 and R2. So now if you expand this kd cos theta plus beta and cos theta minus beta, so what happens then? You get a factor called 2 cos half kd cos theta plus beta. Okay, so this term is called array factor of the antenna array. So antenna array, this has two antennas. So the basic field comes from the single element where both of them are identical antennas. Okay, and this array factor is coming from the orientation of these two antennas, how you feed them. Because you see how, what are the terms here? So kd cos theta, k is the 2 pi by lambda, which is the wave number, comes from which frequency you are operating at. D is the separation or distance between the antennas. Cos theta is nothing but the angle with the, here with the horizon. And beta is the, again, phase difference of the feed of the two antennas. How you feed these two antennas. What is the phase difference? This is where you will have a say. This beta you can actually control by using these phase switches and all. And by them, you can actually control the total electric field at some distance, some point away. Is this understood? Yeah, do you have any question here? Or with me, right? Yeah, I suppose. Okay, so I hope then people understood. So, so the simplest combination what we have is a two element array. Okay. So here if you see the right side picture, let's say two microstrip antenna connected by a feed, and there we have a power divider, right? So here if you see, we are keeping the I naught constant for both the antennas. I naught is the feed signal we are providing, the amplitude of that. So if you have to give the same feed, so we need a power divider of equal ratio. See again, so now how all the things we have learned in the course, how it is coming to be useful. If you have to make a important system, you have to build on antenna, divider, power divider or coupler, phased array or the phase switch. So all these things come together. Okay. So now what happens, if you see here, we have a term 2 into cos theta, okay? Here for the array factor. Now because of using two antennas, the electric field gets doubled. So the power gain is corresponding to the power is square. So it gets four times. So four times in the normal scale or linear scale means in the log scale it is 6 dB improvement. It's right. Okay. So now 6 dB improvement. See what you have to remember now. All the antenna is feed with the same power as same as the single antenna. Previously also you are feeding a one antenna with I naught. Here also you are feeding with I. So what happens? So now you have to actually feed by 2 into the same current, so that the both the antenna divides and get the I naught. Okay. So because power divider is 3 dB division, right? So what happens now? Now the if you see, so you are feeding with two I naught or two of the original current to give the both the antenna same current I naught. So that's why you are compared to the single antenna case, you are feeding with I naught. So you are losing here 3 dB less, but you are getting 6 dB improvement in the gain. So ultimately it's not 6 dB gain, but it's only 3 dB gain. Okay. So now the point is, how does this come from? Where does this game gain extra 3 dB gain or 6 dB gain if you see from this antenna perspective? How does this gain is coming from for a phased array antenna? Yeah. So yeah, I will ask you now. Where do you think it comes from? This gain for a phased array antenna?
Because each of the element is contributing to the field at a point of interest.
Yes, that is right. But I am saying, how does compared to one single antenna, how does it improves? That is right. Obviously, it happens. If you add multiple, it will increase. But how physically it is happening? What is the phenomenon making it happen?
Like, yeah, we are shaping the beam, like instead of having a
Ah,
broader
yes.
beam. Yeah,
Now we are again doing the same thing. I am saying, asking about the physics. What is the physics behind it? Those are what you are saying. This is right. But this is just a phenomena. Yes. But how? What is making it happening? Anybody else? Yes. So somebody has pointed out is right. So constructive interference as well as destructive interference. Hmm. So if you see, if you take only one single patch antenna or only one single horn antenna, what happens? The beam is almost distributed almost equally, not equally. It has a very good coverage, beam coverage over a wide region. Now, if you make a two antenna array of two horn antenna or two microsтрip antenna, you will see because of this, the phase difference we are creating between them. So one side there will be uh, constructive interference, and another side there will be destructive interference. Okay, so because of that only the beam is getting magnified in one direction and getting reduced in another direction. So the main thing is actually the beam or the power or gain is reducing in lot of other direction. So those what is reduced is getting added up to the other zone. Okay, so basically it is because of interference. So those you must have seen in basic physics classes, I hope. Okay. So that is the basic physics about it and two element array. So now we will see like how mathematically we calculate using um, the array factor. Okay. So array factor is very important. You should always remember around this factor. And also it is for a multiple n number of antennas, you will have a factor in terms of e to the power j psi, where psi will be called this kd cos theta plus beta. Okay. So this is just another way of representation. So now for a only two antenna element, it gets simplified and you get this form. Okay. So now let's see three different conditions. Let's say d equals lambda by 4. That means you bring these two antennas at a lambda by 4 distance and beta equals 0. So that means there is no phase difference between them. So now from here, from this array factor formula, if you see here, when the beam will peak. Okay. So yeah, can anybody tell now how do we now get a beam when the beam will peak or when the beam will have a null? How do you calculate from this array factor here formula? How do you calculate it? So we have kd cos theta plus beta term, right? So from here only we can guess which
The
side
mag.
the array will have a maximum and or peak or which side is a null. Yeah. Now you tell me which by calculating which of the facts here in this equation you can calculate it. How do you know which
Yeah, that
direction? Hmm.
by equating that kd cos theta plus beta is like
Hmm.
by taking trigonometric cos limits like one as a maximum, we'll put kd cos theta plus beta by 2 as a um, 0
Yes.
for
Uh,
maximum.
no, I mean, see, cos theta becomes maximum when is the condition for that?
Yeah, when theta is 0 degrees, that is in the
Yes,
broadside.
no, no, or not only zero. You have to take a generalized term.
Yeah,
Okay,
like
so
yeah,
yes,
2 pi, 0 or multiples of
n pi, even
0.
n pi is
Yeah,
also
n
okay.
pi.
Okay, yeah. So now from there you have to take. It becomes n pi. So this in between term kd cos theta plus beta by 2 has to be equals to n pi, right? So if you take at the minimum condition when it becomes 0, so that will not give you anything when beta is also 0. Let's say when beta is 0, cos theta is 0, so that does not happen. So you have to go to higher term. Okay, when you have a pi or plus minus pi. Okay. So like that, if you take here, so beta is 0 here. So kd cos theta by 2 has to be pi. So from that, you get theta equals pi by 2. So obviously cos theta pi by 2 means this term becomes 0 and you get cos 0 is 1. So for theta at pi by 2 direction, you will have peak. That means at the broadside direction, you have a beam peak. And now for a null, what happened? The in between term has to be pi by 2, multiple of pi by 2, odd multiples of pi by 2. 2n plus 1 into pi by 2. That is how we write. So that if you see here, if you solve this equation here, generally it becomes cos theta n equals 2. That does not have any solution. because cos is less than equals 1. So no nulls. Okay. Now let's go to the same thing. D remains same, lambda by 4, and beta equals pi by 2. Now that means we are changing the phase difference. So what happens now? If you calculate the same thing again, the beam null now you see, beam null here is becoming now at pi by 2. So just by feeding them at a phase difference of pi by 2, you are creating now a broadside null. Okay. And your peak direction is under either theta equals 0 or 180. Okay. So that means it's a end fire. You have a end fire antenna now. Another combination is, let's say d equals lambda by 2. Even you can change the distance also. And beta equals 0. So you have another condition for, null and maximum. So which now by looking into these three cases, it says that the direction of beam maximum and nulls can be steered by phasing. So steered by phasing means beam steering, because the peak and null we can steer in some direction of theta by phasing. What is phasing? By giving defined values of beta to these antennas. All right. So that is it. But there are, see, this is one thing. We are just talking about the antenna pattern. If you look into in depth, so there will be other terms like the S11 also has to be there, and there has to be, the mutual interference is also there. So generally, if you take the distance between them less than lambda by 2, the mutual interference is greatly increased. Okay. We generally want to reduce the mutual interference between these two antenna. If one affects another, obviously the beam will get distorted. So you should have generally a distance of lambda by 2 or more between the two antennas to reduce the mutual interference or mutual coupling. That is another aspect of antenna array design. Okay, so before moving on, any question here? Okay. So, this picture just shows the different phased array combinations. So one antenna is reference you take, another antenna is have a extra additional phase. So if you have 0 degree, obviously the beam will have a maximum in the green is the maximum, and there will be some side lobes which is shown in magenta colors. If you have a theta reference, it will move in some direction. And if you give a minus theta, generally because of symmetry of these two antennas, your the beam will move to the other direction. Okay. So these are called the basic structure of phased array, but it's also called coherent phased array. Yeah. Do you know what is coherent means? What is coherence here? Any idea why it is called coherent phased array?
The phase difference is basically it is a length matched, so phase difference of like transmitted phase difference is going to be same for both the lines.
Mm, yeah, transmitted phase difference is there, but no. So how does it make it coherent? Because there is a phase difference, right? So it is not coherent by your terminology. I mean, by your
Means
definition. Yes. Then
elements are like exactly identical, both the elements.
elements, you are saying if we just have two same antennas, it will become coherent.
No, man, like it's like the antenna patterns means like for each element are identical, maybe because of that.
No, no. Generally, this coherence, if you see, it comes from the communication itself. Okay.
Okay,
Mixing of signal.
the reference
Yes,
Means
reference.
like the phase difference between the elements is like having some common reference so that we can have a accurate beam steering.
Ah, that is right. What is that common element?
They have constant phase at all the time.
Mhm. No, no. Phase only we are changing, right? Phase difference. We are playing with the phase only. I'm saying
The
something is
reference is
common.
common. The
Sorry?
reference is common. The reference is common.
Ah,
Is
reference is
0
common is written. What is the reference? Yes. What will you be giving to these antennas which is common? We'll be definitely using a phase shifter here, right? That will have these switches and all. So what is the common here? The antennas can be different, okay? There is no limitation on antennas.
Antenna excitation, like input source.
Ah, exactly. What is that input source? Is the carrier signal what you are putting.
Yeah.
Okay. Yes. So if you see in the communication paradigm, it says the two sources, like receiver, you will have coherent receiver system there. So that means whatever carrier was sent from the transmitter in the receiver also, if you have the same carrier present, okay, then you can match them and you can recover the signal. That is why it's called coherent receiver in a
Right, right.
communication. So exactly here also you are feeding both the antennas with the same carrier signal. So it's not like one carrier you are generating from one oscillator, another carrier you are generating from another oscillator. So if you do that, what happens? Even though they are same company, same batch, everything, they will not be exact. There will be some phase difference between them. So that will make it, a non-ideal. So that's why it's called coherent phased array. You have to feed both the antennas from the same antenna array, it's the same source, same carrier source or same VNA, whatever you are using. So how do you do that? That's why we use a power divider. We give a same carrier signal and divide it and feed to them. That is what we have seen here, right? Here. You see, it's a very simple thing, but that has a lot of implications for a phased array. You might think just a phased array, why it is, much, what is importance, but that is only is making it a coherent antenna signal, both of them. If you don't use them, if you feed them with two different signals, that does not guarantee that you will have a phased array operation. So these are the very basic fundamental things you should understand. Yeah. Okay, so now moving on. So obviously now what are the uses? Now you tell me some application where you think this phased array is useful. Why can you use? Let's say we can steer the beams, right? So what are the application coming to your mind for this?
Radar scanning.
Yes, for detection, the object or DOA determination, right? Yes. And other in communication, what do you think we can use it for?
At receiver section.
Mm, sorry, receiver, how?
Hmm.
If you see in current
No, no,
5G,
no, sorry, transmitter section. Transmitter section, we can.
yes, transmitter section is
Uh,
definitely yes, but how do you use in transmitter section?
at 180 degrees phase shift, 90 degrees.
No, no, all those are fine. I am saying what is the application? What do you think in the real life it can be used for? Those are fine. How you make it that there? Yes. How do you see it?
For broadcasting.
Probably in the base stations we can use it.
Right. Yes, one source can be best to best station. But see, another thing is generally, if you have to send signals from one base station to another, it generally uses a very good link, or maybe they have an optical fiber cable or a underneath ground cable because they don't want any loss there, and it should be very high bandwidth signal between them. Okay. But at the last end, from the base station, the signal is moving, right? Let's say base station, you see the antenna towers, there will be various antennas there. So many of them are actually phased array. They want to cover one particular zone in one direction. Okay, they don't want their beams to be, covered in all other directions. Okay, because nowadays, as we move to higher and higher frequencies, even in current 5G, if you see, we use something called MIMO or massive MIMO, all this.
Correct. Correct.
Yeah. So if you know as we use very higher frequency, the path loss increases. Okay, so we cannot use a one base station antenna for 5-10 kilometer. You just, it does not make sense. You will lose huge amount of power here and there. Okay, so generally in the current scenario, people use very small cells. Cells are like the where the signal will be covered from a base station. You use a very small cell, and the antennas will be having very pointed beam. And if the accordingly, if let's say you have to cater to a moving or autonomous vehicles and all this, drones and all, so you can just track, and accordingly you can move your beam towards that direction, so you will minimize the loss of the signal. And the because of gain in particular direction, because of the phased array, the signal will be reaching, or SNR will be high in that particular direction. Okay, so that is how we are talking about, overcoming the path loss and all in higher frequencies. We need more and more sharp pointed beams so that we don't lose here and there more signals. Yeah. Now, so before moving here, I forgot almost that, I told you I will give you one reference for this, the phased array SPDT switch implementation. I found a paper. You can implement this in ADS. Okay. So this was this, I suppose. Yes. Okay. So this has, ADS also. It shows ADS implement also. So you can just look into this. Just, Okay, so I have uploaded this. So you guys download the file. I hope you can all see this file here. Design of a 90-degree phase shifter, switch line phase shifter. So try to implement it so that you will learn. It shows even biasing line and everything. Okay. Okay. So now moving on. There are many ways you can actually implement a phased array. So by now you understood that only using two antenna you will have some advantage, but it might not have a very sharp beam, or what we call a pencil beam. For that you need multiple antennas or a very big aperture array and all these things. So that's why it gets quite involved or complicated system. So there are multiple defined architecture itself, how you make this kind of phased array. So if somebody is interested, I will suggest, you can go to this paper here. It gives a very good gist of all the phased array architectures. So we'll just see here like 2-3 different things. Somebody was asking yesterday about, analog and digital, right? So here if you see, these are these the first one is digital phased array, and there we have a analog phased array as well here in the next slide. So the difference, if you see the first picture here, we have beamformers or the phase shifters here, which is controlled through analog beamformer. So the moment you put a phase shifter here, that means you have to control it with analog signals, because you need this phase shifter and all these things. That is why this is called analog processing. Okay, so it's kind of a analog. But here also you see, it's not only analog, it has a digital part also. So now the question will come, how do you control it by digitally? Anybody? Yeah, first I will ask you guys. Can you do the same thing? Can you, how can you generate a digital phase shifter? What do you think? So the phase shifter means we have to generate some phase difference, okay, by switching the switches, pin diodes or these things. We have seen that there is a way, right? But now I am saying those are analog way. Without using this, how do you do it in digitally? What do
DAC
you think?
with
Yes.
using DAC.
No, DAC is required, right? Anyway, if you switch or not, anyway, digital to analog converter is required. That will be there, right? Any signal, it will be required. But I am saying, how do you change the phase of this antenna? We generally want to feed these antennas
Digital
with
phase
different
shifters, like
phase shift. Yeah, tell me.
no, like digital phase shifters we'll be using.
No, digital phase shifter is what?
But
What is
you,
digital?
what is internal? Okay,
Yes,
circuitry.
yes. There is no circuitry where the digital means what? Digital means you have to do things in signal processing. Okay, you will have
Yes.
some bit data in your computer or microcontroller, whatever. You have to do some signal processing, right? Digital does not mean any circuitry. The moment you go to circuitry, it becomes like analog processing
Analog.
mostly. Yes. So how do you just do it in digitally?
Time delay.
Time delay or phase delay?
Phase delay.
It's like we can switch each signal on and not off at different times so that we can introduce the shift.
See, you are talking about just phase switching and all this, that will need another switch, right? That will again back to analog signal processing. I am saying, how to do you do it a digital beamforming? So that's why it's called digital signal processing. Okay. You, let's say you don't have any switch or any phase shifter. Okay. How do you do it now?
We just change the phase while there is no change in the signal's power level or amplitude, probably.
No. So how do you change the phase? That is what I'm pointing at. See, I don't know if you have seen the normal communication, how it happens, signal processing. You have a in phase and quadrature signal, okay, that is generated as baseband, which is called baseband signal. So those signals gets multiplied with the carrier signal, the oscillator.
IQ,
Yes,
IQ, uh,
yes.
IQ. That is only.
Yeah, now I'm coming there. See, now how
Uh,
it's related. All communication, everything is like converges at one point, right? See, I and Q, these two signals, these are baseband. So these two, whatever we generate from your computer or microcontroller, okay? So this data I and Q, what you provide, it gets multiplied to your carrier signal, and then it's added up and transmitted through the antenna. That is what happens. Now, okay. Now let's say instead of this I and Q, you give your baseband data only what you provide from your computer, a shifted version, e to the power, let's say pi by 4 phase shifted version with I and Q together. So that will get multiplied to carrier and will give the same thing what you are doing in analog phase shifter. Okay. So these values what you generate, this in phase and quadrature value from your signal processing will give the same thing. It will generate the same effect. Okay. So that is kind of digital beamforming. Understood? So this
by
is kind
using
of
mixers. By using mixers,
Yes,
I think.
yes. Mixer is required. So mixer is required for communication, right? Yes. So if you see the signal actually communication receiver, it will be I into cos 2 pi FCT. FC is the carrier plus Q into sine 2 pi fct. Okay, so in phase and quadrature signal is generated from your laptop or PC or whatever. In from digital signal processing, what you generate will get multiplied to the board using a mixer, and then gets added up and transmitted to the carrier or through the an- antenna. But there are other modulation and other things, filtering and all. But the main basic thing is this. The same thing is can also be used here for generating a phase shift between the antennas, just by giving a phase shifted version to your baseband signal. Okay, that is called digital beamformer. Now there are many different scenarios here. So if you have multiple antennas here, you see here. Generally, see, if you want to generate this kind of antenna, you are not like only for transmit, right? We generally want transmit and receive both to be done through the same antenna system. Okay, we let's say we don't have space for 10 different antennas, one transmit, one receive. If we generally want transmit receive together, that is why you see there will be like beamformer ICs and all that comes like hub duplex. Okay, here if you see inside the antenna block, what is there? There is one amplifier for the transmit path. There is a circulator, okay, or limiter, which isolates the transmit and receive path. Okay, one time it will transmit, another time it will receive. Okay, so this scenario is called half duplex. Either transmit or other receive, or also you can call time duplex signal. So using this same phase data, you can transmit as well as receive. Okay. Now, this is one part. You can use this individual antenna separately and multiple beamformers. One thing you can use. And another way is that, the people have, there is a lot of research on that you can divide the multiple antennas into sub arrays. You take some two antennas and as an array, three of these two antennas as a defined array. These are called sub arrays inside a big array. By feeding them differently, intelligently, you can make lot of different beams, lot of intelligent operations. Okay, so these are like the operations or like lot of options available there. But mainly here, if you see, the architecture is called here digital beamformer as well as analog beamformer. And the right side, it is only digital beamformer. There is no phase shifter here, if you see. Okay. Now, if you see this side, this is analog phased array. Why? This is completely analog beamformer. Okay. And the right side again we have analog beamformer as well. And but you are feeding it differently, and it has transmit receive both full hub duplex. So this is called passive phased array left side, and the right side is active phased array. Active, why? Because they has amplifiers here in the full hub duplex, so transmit and receive. That's why it's active phased array. So there are many different ways, and if you see actually the circuits, the complete phased array circuit, it is actually looks it is quite compact. It has lot of elements into one circuit board. Okay, but basically it will have all these elements. Okay, but yeah, any doubt here?
Once go to block diagram.
This one.
No, back. Before you went now phase shifter everything. No.
Oh, this one.
Ah,
Yeah.
it's this as this.
Mhm. So the here if you see, the feed is what is feeding the signal, right? Actual carrier signal is coming here, and then it has lot of power dividers here. So power is getting divided, and in between we have phase shifters. These yellow blocks in between are the phase shifters, and those are all controlled through a controller, microcontroller board, let's say. So by controlling this, you will generate some phase here and there, and that will give you the operation what you need. The beam you want some direction, null in some direction, that will be generated. So let's say this is like a 8 antenna array. Okay. So you have even 16 antenna array. All these are possible.
So same concept. It is like a phase correlator. Sir.
Phase correlator, is it used in communication receiver?
Yes, sir. The transmit, yes, sir. Yes, receiver section only. Yes.
Yes, yes. It is kind
Yes,
of
sir.
same. Correlator is
Uh,
generally, nothing but integrator and all because
yes,
yes, you have
same
to
concept looking like.
might be yes because see so all are related. Like nothing is different here. So everywhere you need a microcontroller to control signals. You need a carrier signal in communication as well as here everything. Because ultimately, see these phased array where will you use? You will use at the end of a transceiver chain only, right? Or at the beginning of a receiver chain. So it will be all integrated either to a communication system or to a radar system. Okay. So other things will also be there. So there will be always problem with phase synchronization. How do you make it coherent? All these things will be there. So other blocks remain there. Okay. So today, today we'll stop it here. And next week again we'll go to the phase shifter. We'll start from how a phase shifter can be implemented. Okay. So we'll look into that. In between, you do the assignment and please submit by next Saturday. Okay. And you do it. Uh, so today we'll end it here. Okay. And tomorrow, not tomorrow, next Saturday we'll meet again. And I have given you this new paper also. You look into this. So then you will understand how actually it can be implemented.
Sir, by today